Welcome back to the course page on digital signal processing. So let us review. So a continuous time signal will give you an aperiodic spectrum. A discrete time signal will give you a periodic spectrum. A periodic signal will give you a discrete spectrum, and an aperiodic signal will give you a continuous spectrum. Now let us look on a summary of these two cases. One is discrete time Fourier transform and discrete time Fourier series. In case of a discrete time Fourier series, it's periodic and it is discrete. We obtained a periodic and a discrete spectrum in the frequency domain. So for that we used an equation x of n, which is a time domain signal. X of n discrete time domain signal in x of n is a sequence which is equal to sum of k is equal to from 0 to n minus 1 into x of k, which is the frequency component, and into e raised to j2 pi k n by n. And so that's how we got the discrete time Fourier series. Discrete time Fourier series here it is discrete and it is periodic. So we'll use to convert this signal into the frequency domain, we'll use x of n. X of k. X of k is the frequency coefficients, and it's equal to 1 by n into summation of n is equal to 0 to n minus 1 x of n into e raised to minus j2 pi k n by n. Now for the synthesis we'll use x of n. Small x of n is a sequence which is in the time domain, frequency domain into time domain. We'll use this equation. Similarly, for a aperiodic signal which is discrete in time and it is aperiodic, we'll use a discrete time Fourier transform method. So what happens is, since the signal is discrete, so we'll get a periodic spectrum, but the signal is aperiodic, we'll get a continuous spectrum. So the equation for converting these time domain into frequency domain or the Fourier domain, we use an equation x of omega is equal to summation n is equal to minus infinity to plus infinity x of n into e raised to minus j omega n. And for the synthesis in the time domain, we'll use a x of n is equal to 1 by 2 pi into integral of minus pi to pi x of omega into e raised to j omega n. Okay, so these are the two equations. Why we use in integration? Because it's a continuous time. That's why we use for the integral signal here. Here, now see here. Here we obtained a frequency spectrum. This is the frequency spectrum for a aperiodic discrete signal. Now the question is this: how can we store this continuous spectrum in a digital computer? Normally the signals are stored in terms of the samples or the discrete. We can use a discrete. Everything is stored as a discrete samples. So it's very difficult. Then what we will do is we will sample the signal in the frequency domain, and in all these cases we sample the signal in the time domain. Now the case is we need to sample this signal in the frequency domain, and the resulting will be the discrete Fourier transform. We'll see now how discrete Fourier transform is. So let us recall this. Aperiodic in time, we'll get in the frequency domain, it's a continuous in frequency. X of n becomes a continuous frequency. So x of omega will got an x of omega. X of omega is continuous in frequency, but this x of omega cannot therefore be computed for the entire set of omega. And for practicality, x of omega must be computed for discrete. and a finite set of values of this omega. എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ അപീരിയോഡിക് ആയിട്ട് ടൈം ഡൊമെയിനിൽ അപീരിയോഡിക് ആയിരുന്നു സിഗ്നൽ, ഡിസ്ക്രീറ്റ് ടൈം അപീരിയോഡിക് സിഗ്നൽ ആയിരുന്നു. വി ഒബ്റ്റെയിൻഡ് എ കണ്ടിന്യൂസ് സ്പെക്ട്രം ഇൻ ദ ഫ്രീക്വൻസി ഡൊമെയിൻ. കണ്ടിന്യൂസ് ഫ്രീക്വൻസി ഡൊമെയിനിൽ ഒരു കണ്ടിന്യൂസ് സ്പെക്ട്രം ആണെങ്കിൽ അതിൽ ഇറ്റ് കണ്ടെയ്ൻസ് ഇൻഫൈനൈറ്റ് നമ്പർ ഓഫ് ഫ്രീക്വൻസി കമ്പോണൻസ്. ബട്ട് ഹൗ ക്യാൻ വി സ്റ്റോർ ദീസ് ഇൻഫൈനൈറ്റ് number of frequency components in a digital computer, and we are using a digital computer, so it's very difficult. So what we will do is we will sample this signal and in the frequency domain, and we will use and store the frequency component. That's why we call it as a discrete and finite set of values. So the method used for this is what we call it as the discrete Fourier transform. So the strategy to compute this x of omega is compute x of omega for equally spaced samples. So we'll sample this x of omega. X of omega means it's a frequency domain signal, and this frequency domain signal is equally spaced. And compute the x of omega samples for one period only. We know that in case of a discrete time Fourier transform, we got a spectrum of continuous and a periodic spectrum. So we need to compute only in the one period. So suppose we are computing n samples of x of omega over one period of time, or from 0 to 2 pi, then the resulting computed frequency of the signal would effectively be a sampled version of x of omega. That means omega is equal to 2 pi by n. Each frequency is being 2 pi by n. If you have n number of samples, then we will divide the 2 pi into n samples. So each frequency is omega is equal to 2 pi by n. Yes, here I have illustrated the frequency domain sampling, and see here, from this place to this one, this is what we call it as the 2 pi. The same signal is repeated, and we'll take n number of samples up to this point. From 0 to up to this point, we'll take n number of points, and so the spacing between each of the sample is, in between these two samples is, it's equal to 2 pi by n. So that is what we call it as the frequency domain sampling. Now here we will recall the discrete time Fourier transform, discrete time Fourier transform DTFT. So in this case, x of n is equal to, x of n can be written as, it's equal to 1 by 2 pi into integral from minus pi to pi x of omega into e raised to j omega n d omega. And for the frequency samples, x of omega is equal to, the analysis equation is summation n is equal to minus infinity to plus infinity x of n into e raised to minus j omega n. Suppose we sample this x of omega according to omega is equal to 2 pi k by n. We'll sample the sequence in the frequency domain. So here, instead of omega, we will replace by, we know x of omega is equal to n is equal to minus infinity to plus infinity x of n into e raised to minus j omega n. So instead of omega, we will use this 2 pi by n into k. So substitute omega is equal to 2 pi k n by n. So 2 pi k by n. So we'll get the equation as this one, and let and here it is equal to n dash is equal to some n minus in. Okay. Here it is, I have some confusion is here.